Nope. Okay, well, pull me off to the side. Okay, so today we are going to be jumping into, what section is it? 2.2, which is separable differential equations. So we got a little bit behind, but we'll be able to do 2.2 and 2.3 today. That is 2.2. So I'd like to start our discussion of separable DEs with an example before we talk about why it works, because I think separable DEs are almost really intuitive. They can get challenging, but the simple examples are really intuitive. So let's start with a good example. So for our first example, we're going to have dy over dx equals x over y. And our goal is going to be to move the y's to the left and the x's to the right. So algebraically here, the only thing I need to do to get the y's on the right is multiply both sides by y. So I have y dy dx equals x. And now what we're going to do is we are going to kind of use the notation to our advantage and kind of like pretend that dy is a variable. So we'll show that that's actually not what's going on, but we're going to pretend and that dy and dx are variables. So I'm just going to multiply both sides by dx. And when I multiply both sides by dx, I get y dy equals x dx. So I have x's on one side, y on another. And now, if I just throw in my integral symbol, I can take the integral of both sides. So the integral of y is 1/2 y squared. The integral of x is 1/2 x squared, and you only need the plus c on one side. We just generally put it on the x. Now, I forgot to give you the initial condition for this one. So let's do the initial condition of y of 0 equals -2. So this is kind of a choose your own adventure in terms of like you can solve for c right now, or you can solve for y and then plug in for c. Sometimes it makes sense to solve for c earlier than others because sometimes the solving for y actually makes the equation more complicated, right? But so we can practice dealing with c's. I'm going to solve for y and then we'll substitute in to find the c. So I'm going to multiply everything by 2. So I have y squared equals x squared plus, and then I technically have a 2c here, right? But this is just some constant times a 2. A constant times a 2 is going to be what? Another constant. So do we write 2c or do we normally just write c? Yeah. Okay. And then I'm going to take the square root of both sides. So I have y equals plus or minus the square root of x squared plus c. You have to be careful with this. You can't write x plus c because the square root of a plus b does not equal the square root of a plus the square root of b. So we can't break it up and absorb that square root into the c. So this one we do have to leave. And then we have both roots, right? So now when we're solving for c, we're going to have to choose which root we want. We want the positive or the negative. So looking at our initial condition of y of 0 equals -2, are we going to want the positive root or the negative root? Negative. Why, Theo? Perfect. So I have -2 equals, and the only way for that to be negative is to take my negative square root of 0 squared plus c, and then we could solve that down and get c equals 4. So then our final answer is y equals the negative square root of x squared plus 4. And since we made that choice of to satisfy our initial condition, we need a negative, and our answer, we're also going to need a negative. Okay. How do we feel about that? Okay. So one thing we do have to check is where is this solution valid? Because square roots can sometimes cause issues, right? So we want to check where is x squared plus 4 greater than 0? Well, x squared is always going to give me a positive, 4 is a positive. So is this quantity always going to be greater than 0? So that's fine. So this is always true. So we don't have an issue with the square root, but we also have to be careful because in our original differential equation, y can't be 0, right? And so this quantity, which gives me y, is always going to be greater than 0. It's never going to be 0, but it's just something you have to check. This one worked out that the answer is going to be all real numbers, but we do need to check that. So the negative square root of x squared plus 4 never equals 0, and y can't equal 0 since dy over dx, equals x over y. So the interval of validity is negative infinity to infinity. There are definitely times when that is not the answer, so we do have to double check that. So I think the natural question here is, why does this work, right? Because dy over dx is notation. It's not a variable. So we can't just multiply both sides by dx, but that's kind of what we did, right? So why does this work? Why can we do this? So let's say we have a function n of y times dy dx equals m of x. So the reason we're going to be able to do this separation of variables comes from the chain rule. So let's recall our chain rule. So if we have f of y, where y is also a function, y of x, then using this notation, does anybody remember what df dx is? Yeah, y prime x times x prime. I think you're almost there. So it's the derivative of f with respect to y times the derivative of y with respect to x, right? Because we take the derivative of the outside with respect to our initial variables and then the derivative of the inside. So let's kind of match it up to the n's and m's we wrote above. So df dx is m, df dy is n, and then dy dx is dy dx still. So we have the derivative of f with respect to x, I said was m, just matching. And then what that means is the integral of df with respect to x, integrating with respect to x, is going to equal the integral of m integrating with respect to x. So if you have a derivative with respect to one variable and you're integrating with respect to that variable, what's the integral? Just f of y, right? Because if you have like the integral of y prime, you get y. So we're just back to f. So we have f of y equals, and then there's nothing we can do to simplify this. This is still the integral of m. So this is one thing that we know f equals. Okay. But then on the other hand, we know that df of y, derivative with respect to y equals n, right? That's just the correspondence I wrote in red down below. So these are functions of y. So let's go ahead and integrate with respect to y. So if I take the integral of df of y over dy with respect to y, and the integral of n with respect to y, what's going to happen on the left? We're left with f of y, exactly. You're taking the integral of a derivative, so you're just left with the function. That's the fundamental theorem of calculus, I think. And we've got integral of ny dy. So we have two things that f equals. So we can conclude that the integral of n of y equals the integral of m of x dx. So when we were solving the problem, what did we do? We just skip to this step. Right? We put our y's on one side, we put our x's on the other, and then we integrated both sides. This is why it works, because we were kind of being loosey-goosey with notation, multiplying by dx, but this is why it works. So we just did a little mini proof. I understand you might still be wrapping your head around this proof. What I need you to remember is to solve these separable differential equations, we are just going to separate y's on one side, x's on the other, then integrate both sides. Yes.
How do we know if there's something look like it, or is there something that
They will just look separate. So you may have to play around with algebra, but your goal is to get something that looks like a function of y dy and then a function of x, and then you'll move the dx over. So you may have to do some algebra, you may have to factor some things out and do some division, but that is the goal. Okay. Any other questions? Let's go to boards and do number 3 on your in-class assignment.